then only the people who have sent me their emails will have access to those videos. If you haven't sent me your email, a personal email, then you won't be able, you'll be able to see it. So you must send me your personal email to watch those recordings. So welcome to the first session of our intensive revision classes. So we're gonna start with chapters 1 to 3 inside this session, right? Then chapters 4 to 6 in the evening. So let's start. So I'm gonna explain a lot of theory here, right? Yeah, this thing needs me to drink some coffee. Let me drink. Yeah. So this thing is gonna need you to like be very patient because there's a lot of things to define here. So what is the whole, we're gonna start with what is the whole purpose of programming and computer science? Why are we doing all of that? That's where we're starting. So in order for us to understand all those things, we need to start by understanding what is programming, right? That because that's what that's what you guys are doing right now. You're doing something that we call programming. So programming is basically the art of solving the real world problems, right? You take real world problems that are in the physical world, right? In the world me and you live in, right? You take those problems, then you solve those problems by making the art of solving real world problems by making software, or sometimes it's called a program, right? By making a software or program as the solution, right? So basically, you look for a problem that needs solving, then you make something that we call software or a program. Software program for you guys, you know it as an app, right? Like Instagram, TikTok. This is just a fancy way of saying it's a software program, but the right IT terminology for it is a software or program. App is like, you can think of it as like a slang in a way for software or program, but we basically referring to the software or program. So basically the app itself, where it has buttons and the place to record, if it's a recording app, all those things, that's what we call the software or problem or program, right? It solves a specific problem. So if you think about it, this is definitely true because if you think about back in the days before all of us were even born or even our parents thought of bringing us into this world, way before they even that thought even occurred to them to their mind. People used to send or communicate via emails, right? Or letters. So they'll write a letter, and that letter would be, for example, hey, how are you? Right? So that would be the letter. Then it might take in something from a week to like 3 months or so just for them to receive that letter, depending on the distance. Because remember back in the days, there were no things like Google Maps, all those stuff. You just take a map and then you just hope for the best. That's basically it. So you just take a map, hope for the best. You hope you find where you reach where you want to go. You reach your destination. So that's how they used to communicate, and there'll be delays in the message. What if it's something important? Like, for example, there's a funeral in 2 days. Can you please attend? We're inviting all family members from all parts of the world to come and attend the funeral. If that message takes at least a month or 3 months to reach, that means you host the funeral without the important family members. What if the father wrote some letter and said, okay, so and so will be receiving my cows, so and so will be receiving my horses, so and so will be receiving my clothes, so and so will be receiving this. So all members or family members need to be there. So that's when developers, right? Basically, the people who make this software, right? They're called software. Another word for making, right? They use the word develop. I used the wrong term there. Try to use the right term. So I just said making to make it simple for you guys. It's like you have a bunch of Legos, right? And you're making a building or a car using Legos, right? So it's basically similar. It's same thing. But then here we use the term develop software. So it's the art of solving real world problem by making or developing software or a program as the solution to that problem. So those people who make those things, basically you and me, the people who do the prex, people who do the implementation and everything, those are called software developers, right? So these software developers decided to sit down and come up with a way to bridge that gap, right? So that you get when you send a message, you receive it instantly, like it's an instant thing. Then some people came up with things like SMSs. Then they realized SMSs are quite costly because you're gonna have to use a lot of airtime to communicate. And the longer the paragraphs, the more the airtime is going to consume. Then people are like, okay, let's try to make an app like Mixit. Then they made an app like Mixit. Then apps like Instagram started to emerge. Apps like WhatsApp started to emerge. And then now communication, what's that word? We bridged that communication gap, right? We couldn't communicate from long distances, right? But then until that day when they invented the apps, we're now able to communicate with our loved ones or relatives or whatever, or lovers or whatever the case may be for you. So they were able to now communicate. So this is the whole process. So that's basically what you guys are doing. Is look for a real problem, then you solve it using making an app, or the right terminology for it is software or a program. So in order for us to understand all these things, we need to understand a little bit, just a little bit, about the hardware, right? So a computer, right? When you look at a computer is made up of two things: software and hardware, right? So software is basically soft things, right? So basically non-tangible things, right? Or basically non-visible. These are things that are not that are not, I shouldn't say visible. Yeah, technically it is visible, technically. That's the terminology they use in the textbook. They say non-visible, but you can somewhat argue, but it's fine. We're just gonna use that definition. So these are the non-physical, but I wouldn't use visible. I would say the things that are not physical. Yeah, I would say non-physical, not non-visible, because for example, you can see this app, right? You can see this Chrome. So it is visible. So you can't say non-visible. Not me trying to correct a whole author. But yeah, to me, that's how I would view that. I would say it's non-physical, not really non-visible, because it is visible to the naked eye. You can see it, right? You can see what I'm typing. You can see my screen, right? That's software. I'm using Notepad++. That's an app, but you can see the app, right? You can see what I'm typing. So it is visible. So, but like I said, this is not direct, it's not proper. It kind of makes sense. I don't want to throw shade, but it kind of makes sense why certain things in the textbook are not. He doesn't use proper English, because that the author is actually, I think, is Chinese or Korean, but he's Asian. So it's not his mother tongue. So I wouldn't use this word. Just saying it's not non-physical parts. That's what we call software. So it's non-physical. I'd rather use the non-physical. Then hardware is the physical parts, right? Or components. They use the word components, which is just another word for parts, components, right? So these are basically when you open your computer, the things that you see inside the computer, that's what we call hardware. It's the physical parts. When you switch on the laptop, whatever you see there, that's what we call software. Even the operating system itself is called software, because it's non-tangible. You can't touch it. It's inside it's inside the hardware, right? You cannot touch it. But the physical parts, you can touch them, right? So I hope that's clear. So a computer is made up of these two things, and each computer has a certain list of things that it uses to manage the day-to-day tasks that you execute using an operating system. Remember, when you use an operating system, you do things like word processing, right? Going inside Microsoft Word, writing an assignment, referencing, all those things for those doing business management. doing all of those things, you're using Microsoft Word, then you also open Eclipse to code. So you using software, so we need to understand those two parts. You need to understand how the software works hand in hand with the hardware. So the main reason of an operating system, right, is so that we can control this hardware, the physical parts. We use what we call an OS for short, or an operating system. We use that to control the hardware components. Because if you don't use an operating system, that means you'd have to control them manually using your hands. And remember that a computer stores electricity. What if you get electrocuted? It becomes a problem, right? So that's why they made an operating system which serves as like an intermediary between the user and the hardware. So it acts like the middleman between you, the person using the computer, and the hardware itself, the physical parts of the computer. So that's the operating system. So the operating system, it works with certain parts of the hardware. The parts that we're going to talk about is this. We're going to talk about CPU, main memory, secondary memory, right? Or primary. Yeah, I think it's called, is it no, I think it's secondary. Secondary memory, right? Then we have input devices, and then output devices. Then I think I'm missing something. What else am I missing? And communication devices. So communication devices. So this is what we're going to talk about. Then it is something that brings all of these things together. We call that a system bus, or just bus for short, right? Not the bus, the school bus, not the school bus. But you can somewhat picture it in that way. So let me show you how it looks under the hood, right? The hardware. Mind you, this knowledge might feel like it's useless, ne? Trust me, you're gonna feel like nobody's business in ComSci 3B if you think this information is useless. Because in ComSci 3B, you're only talking about hardware. That's what that whole semester is all about. You see about CPU, they'll ask you this definition. What is a CPU? What is main memory? Draw the diagram to represent it. ComSci 3B, it goes down. As the ones who have done it before and failed. The thing is, students, they just want to get straight to coding and if statements. No, it doesn't go straight there. You start with the foundation so to understand how all these things connect together. So here I'm going to have a CPU. Yeah, don't take this lesson lightly, or else, yeah, you'll be repeating ComSci 3B. And now the lecturer who was very good in tutoring it or teaching it to Doit, Dr. Dudoit, is no longer here at UJ. So yeah, y'all are cooked. So if you have time to joke around, also the marks will come as a joke. So secondary memory, right? So this is secondary memory, and then it doesn't matter in what order I put them, right? I'm just trying to show you like an illustration of how it might look like in your computer. If you are brave enough, right, you can buy a very cheap computer, you unpack it, you open it, and you learn about each physical part, each part of the computer, of the hardware. You can do that. Maybe buy a computer for 2,000 whatever, but then we are not rich kids, so we don't have that luxury. Maybe when you're doing your final year, when you're doing ComSci 3B, that's when it's really, really important to understand them. So we have CPU input and output devices. So input device, and then we have this over here. It seems like people have issues now with Microsoft Teams. I don't know why it does that. If I had another software that I can use to have sessions, I think I would use that. I'll try and check and do my research. And then we have output devices here. It doesn't mean this is how it's ordered, right? I'm just ordering it in this way, randomly, right? So output device, then we have communication devices. Communication devices, right? These are the devices that help you connect to Wi-Fi. anything related with networking, you would do that in the second semester, Wi-Fi. Yeah, it goes down, Buffett. This time around, there's no what you'll miss those image, UJ image. You'll miss them. Now it's chai, the theory that's there. You can't pass it without reading the textbook. You're gonna learn how to make something. Sorry about that. I don't know. My mic just muted. So I was saying that communication devices, right? These are the these are the physical parts in Teams is weird. Yeah, so as I was saying, communication devices, right? They help the computer to be able to connect to Wi-Fi, to your Wi-Fi router, right? Anything that's related to Wi-Fi, internet, it uses things that we call communication devices. Then you might ask yourself, how do all these parts, physical parts, communicate with one another, right? There's something that we call a system bus. You can view it as like a road. I want you to picture all of these physical parts as houses, right? All of these are houses. So if you want to communicate with this specific neighbor, you'd have to enter this road, right? And then travel and then go to that neighbor, right? So that same, how would I demonstrate this? But then it's fine. Let me try to draw it like this, right? So this is the system bus, right? It's just like a straight line or like a road. That's why I said picture it as a road. It's like a it's like a road whereby this will be the system bus, right? So what happens is that when you're working with the computer, right, when you're executing something, each of these parts, right, they communicate with one another. So for example, let me explain the process when you're running a program, right? So when you open an app, right? Let's say you want to open Microsoft Excel, right? And then this app is open, right? So what had happened is that when the app was loading, it was taken from secondary memory, which we call non-volatile memory, right? So it's taken from secondary memory, which we call non-volatile memory. If this was ComSci 3B, I would be cooked because this you'd have to remember all these things. And then main memory is what we call volatile. So what do we mean by volatile? Volatile, it means that when the electricity is gone, are the things that are stored there, do they still remain there when the electricity is gone? Remember, like I was explaining, a computer, it works with electricity. It stores electricity, right? And then it uses the electricity to give you access to the operating system. Basically, its life force is electricity. Just like when you want uh, to rejuvenate, right? Or to what's an easier word? When you want to refresh, right? Let's say you're tired, agree you go to sleep. That's how you re-energize, right? You just go to sleep and then you wake up. A computer doesn't go to sleep. You feed it electricity. That's like its own way of sleeping. So what happens is that when you switch off or when the battery is low and the laptop switches off, there's always two types of memories that it has. There's one whereby things are stored permanently so that even if the power is gone, right, things are still saved. That's why when you switch on, when you switch off your computer, if you had apps running here, right, you notice that when it opens up again, your operating system, these apps are closed. Why? Because they were stored in main memory. Everything that runs, it gets stored in main memory because main memory is actually faster than secondary memory, but it has its limitations. We cannot store things there permanently. It stores things there temporarily. So that means if I was to switch off the laptop, things that are stored inside main memory will disappear. Everything will disappear. It'll be empty. That's why we have a backup. It's like for example, in this load shedding, if you have a backup, you have a generate, something like that. So the operating system, the people who came up with operating system, the backup. What if you want to store files, for example, right? You wouldn't want this thing of when every time you switch off the computer, it deletes all the textbook you've downloaded, right? That wouldn't be nice. Then you have to re-download them again. So that means you have to make sure your laptop doesn't switch off. That's a lot of work. So that's why the developers who made operating system, they came up with these two approaches. Since secondary storage is slower, or secondary memory, it's slower, we just use it to store things permanently there. Main memory is faster, we use it to run our apps. So that's what I was explaining here. When you type Excel and you say open here, Excel, what the operating system does, right? It's gonna go to your folders or the secondary storage. That's where all these apps are stored. If you notice, every time you install an app, it asks you where to save it because it's stored on your examples of secondary storage, right? It's a hard drive or SSD so that you can picture it. So this would be my hard drive. I have an SSD, so this is my storage, right? So if I go to program files here, I'll find all the apps. There's code blocks here. So what happens is that when I open code blocks and I search for code blocks here, right? There's the app. The operating system, it goes into the secondary storage, which is my SSD, and it looks for the app codeblocks.exe. There it is here. Then this codeblocks.exe gets loaded into main memory, right? It gets loaded into main memory. And also the data that app works with, it gets stored in main memory. Then once it's done, once you go here and you say close and you press X to close it, it removes it from main memory, right? But then remember, it's still stored permanently inside secondary storage, which is your SSD or hard drive. So we don't have to worry about the fact that what if it gets removed, that means I'll have to reinstall the app, right? It wouldn't work, right? Imagine every time you install an app, you can only run it as long as your laptop still has electricity, right? Or power or battery. When it switches off, the app is gone. That wouldn't be convenient. So these two things work hand in hand. So this system bus, it allows us to transport that app. So like I said, when you search for code blocks, the operating system looks for an app called codeblocks.exe, right? Then that app, it's stored, remember, stored inside my SSD, and then it gets loaded into this sort of like a road, and then it travels via the system bus, and then it's loaded into main memory. Then as long as it's running, it's still stored in main memory. And remember, it didn't take the app. It just made a copy of this executable and then transferred it there. So don't expect it to put it back. No, it's already there. You just made a copy of that executable. And then it made it travel via the system bus to the main memory. Then this Murena over here, this guy, the CPU, he is the one who runs whatever this app is telling the operating system to do. For example, if this button is clicked, open this. This is what the CPU does. It's called the central processing unit. In other words, it's the brain of the computer. If a computer had a brain, of which it has, it's actually called the CPU, the central processing unit, meaning everything that has to be processed. For example, running apps and all these things. The main memory, all it does is to store the app that is going to be run. That's all. Then the CPU runs it. That's why you see it under here, down here, and it loads, right? Because the CPU loaded that program. So inside here, the CPU reads whatever is inside the main memory. It says, oh, you want to open this app, and then it launches the CodeBlocks app. But then it's still in main memory, right? That's where it's stored while it's running. Then when you click close, for example, if I was to close Notepad here, right, and I click close, what happens is that it gets deleted from main memory. You don't have to worry. We don't have to worry about where it stores it. Can the person who's unmuted mute? You're disturbing my train of thought. So when this app is stored, when it's done being used, right, when you close it, just know it travels via the system bus. And just imagine there's a garbage can here somewhere, and then it gets stored in the garbage there. Because remember, this was a copy. It wasn't the original. It was just a copy. It travels via the system bus and gets stored somewhere there. So that's pretty much the flow, right? So now, since we have an understanding of all these things, right, and then input devices, right, these are the devices that allow you to that allow the computer or the operating system to receive input. For example, a keyboard when you're typing, right, the operating system receives that as input. Or a mouse, you see that I'm moving my mouse here, it acts as input. Then output is a thing that is used to display something to the user. For example, the monitor, the screen that you're seeing right now, we call this the monitor. So the monitor is one of the output devices that allows us to receive output as the user of that operating system. You can also redirect it to things like files. You can also work with that. This input device would be a file instead of a keyboard. That's up to you. We call that redirection, right? You don't have to talk about that yet. Then you have output device. Then communication devices, right? It allows us to deal with anything that's related to Wi-Fi. Anything that says Wi-Fi is handled by these communication devices. If you read the textbook, it talks about DSL, digital subscriber line, and then dial-up modem, and then cable modem. Yeah, it gives you a list of those things, right? Examples. But you have to understand this part is mainly important for you guys in ComSci 2B. You're gonna learn about Wi-Fi making, and JavaFX is also there. You're gonna be making apps that talk to each other. Yeah, so y'all better be prepared. So we understand everything, right? The central processing unit, right? It remember we say that's the app that's the hardware or the part in our hardware that allows us to run the apps or do some calculations, whatever, because it's the brain of the computer. So the CPU, right? Since it's the brain of the computer, remember CPU stands for Central Processing Unit. So basically, that's where the processing is done. So the central processing unit, it has two things, right? It has the ALU and then the CU, right? The ALU, right, is it stands for arithmetic and logic unit. That's the part of the CPU or the part of the brain that does the calculations for arithmetic maths. So in your code, if you say if you use plus, divide, the CPU, it has a section of its brain that only does arithmetic. If you do if statements, there's a logic unit that's there. Then we have the CU, right, or the control unit, right, which allows the operating system to control things, right? For example, you want to run the app that's stored in main memory. That's an example of controlling, right? It's controlling that app. So it's going to read from main memory, control that app to run it, then it runs it. So that's basically what control is all about. But we will mainly focus on this part, the arithmetic and logic unit. And I want you to understand something very important before we get to data types and variables and if statements. The CPU, right? I was reading, this is not in the textbook. I was reading a course that I was doing on Coursera, and I was learning about C programming. And that course has a lot of theory, but it helped. There's also things like Abo Mantisa, all those things. You don't have to worry about that, but I just want you to understand how the CPU works. The CPU, right? It has a part. Remember, we said it does arithmetic. The part that it does arithmetic on, you actually see this very well in assembly because you can add an integer and a float. You can mix them. The CPU, the way it works is that you can only do arithmetic on the same data types, right? That's how it works. Now you start to understand why we have things like casting. Basically, what this means when I say you only do that arithmetic for the same data type. That means you can only add an int with an int. And you can also add only a float with a float, and only a double with a double, only a char with a char. You get the point. That's basically how the CPU works. This is the trick that took me time to understand. I only learned about it last year or this year, early this year, I'm not sure. So I'm gonna give it to you guys so that you understand why we have things like casting. Because the CPU only performs arithmetic on the same data types. So you can't say perform perform an arithmetic on the data type int and float. It won't work. What would happen, right? The CPU will intervene. It will do what we call implicit casting, which is basically it's going to promote one of the data types. Depending on how big it is, it's going to choose the bigger one. In this case, if I have an int and a float is bigger than an int. So it's going to promote the int to a float. Then it does float and float arithmetic. That's basically how it does it. If you want to do what we call explicit casting, that means you want to do it manually. Usually that's when you're trying to store a variable of a data type that's bigger. You want to store it into the variable of a data type that's smaller. So there's some loss of information there. You can't try to fit in something that's big into something that's small. Yeah, you can't do that. So the compiler, let me just say the compiler or Java, forces you to cast because you are trying to do the impossible. You can't fit something that's very big into a small place. So for example, you can't pack a car in a microwave, right? Why can't you do that? Because the car is very big, it's too big. You can't fit there. So you can't do that. So since you can't do that, it's gonna force you to treat to cast it casting, right? It's sort of a way to shrink the size in a way. So imagine if in a perfect world it was possible. You really wanted to pack the car in the microwave. You can cast the car to something that fits inside the microwave, basically a toy car into a smaller toy car. Then now it would fit in the microwave, right? So in a way, that's what casting does. It does two things. It converts it to a different data type, and it also shrinks it because we're trying to store it into a smaller data type so that it fits, right? So that's basically what we're dealing with here, or talking about. So let's talk about main memory, right? Because we will use main memory most of the time. These other parts, right? They are still there, so working over time for us, but we don't have to worry about those. Our main worry is here because the main memory, you can use it to do two things, right? You can load programs, which is apps that end in the .exe if it's on Windows. And you can also load variables onto main memory or data. So you see that we're going to use it a lot because we're always working with variables in our apps. So I'm going to have main memory here. So main memory, right? So now we need to get to bits or bytes and all those things. So before we talk about main memory, right, we've talked about the different components of the hardware and stuff. So we need to understand how a computer works. How is information represented in a computer? A computer consists of small things that we call transistors, right? These are they are literally electric switches. That's literally what they are, electric switches. Just like your switch in your room right now. When you switch off the light and you switch on the light, it's an electric switch, right? A computer is the same thing. Remember, computers were built by human beings like you and me. So they borrowed from the concept that we are exposed to on a day-to-day basis. So they don't be how do I put it? Don't read a textbook and not relate it to the real world because it's made by people who are trying to relate it to the world you live in, which is Earth, right? So try to link those two things. So transistors, they always represent two states, right? Can either be on or off. In this case, for simplicity purposes, it's not, I'm going to teach you one thing, right? It's not really one or zero, but they like to use that definition to make things simpler for you guys, but it's not necessarily one or zero. If you do if statements in C++ and you really understand them, you know what I mean. I will talk about that. This on and off part, we'll talk about it. So on, in this case, will be represented by the value 1. And then off will be represented by the value 0. Because 0 represents absence of a value, right? Hence, it's going to represent the absence of electricity, or for my physicists out there, current. I think you guys call it current. So there's a presence of electricity or there's no presence of electricity. That's what the transistors do or store. There's millions of them. There's a lot. There's really a lot, like millions of them in your computer. They're very small. So each transistor, it represents a 1 or a 0, meaning there's either electricity or there's no electricity. Now you might ask yourself, how are we going to represent this data? How does it represent even words or letters? How does it achieve that? We'll get to that. So if my computer under the hood, it uses on and off switches, which is ones and zeros, the developers, they simply concluded that the machine language or the mother tongue of the computer, it's what we call binary, right? It speaks in binary. Bi meaning 2, right? 2 what? Values, 1 and a 0. 2 values, binary, right? So that binary, when we have a collection of binary, we call them binary digits, right? So binary digits. So when you have a collection of them, right, can be especially 2 or more. Just say 2 or more because plural digits. So that means it's 2 or more. So when you have a collection of these, we call them binary digits, or in short, we call them bits. The word bits, they got it from the words binary digits. And how did they get that? They simply deleted all of this and they were left with bits. So hence they're called bits in short, which just means binary digits. Basically means zeros and ones. Like I always say, in English, there's a lot of synonyms to. There's why we can have multiple ways to describe one thing. So get used to it. So you have bits, right? And if you have 8 of these bits, right? If you have 8 of these bits, meaning there's 8 of them, so 2, 4, 6, 8. So you have 8 of them, right? These are now what we call a byte, or we can just say it's 1 byte. It's equals to exactly 1 byte, right? That's the terminology you use. So that means if I have 2 of these 8 bits, right? That means if one set of 8 bits is called byte, so this will be 1 byte, right? And then this is also another 1 byte, right? So this is now 2 bytes. So this will be actually called 2 bytes, which is basically 16 zeros and ones. So just keep that in mind. We need to remember this, especially this part of a year, because now I'm going to go to main memory and explain why that's important. Main memory, right? It has shelves. For you guys, I think they're going to, in assembly, they're called registers, but I'm going to use them as pretend they're drawers, right? You keep your personal belongings there. You have a drawer for only socks here. You have a drawer for only shoes here. That's if you store shoes in your drawer. Then you have a drawer for t-shirts, maybe only green t-shirts. Let's say you're really that rich. You have a drawer for each specific color of clothes. Let's just say that's the case, but imagine these are drawers. So that's how the main memory looks. Each drawer is actually of size 1 byte, right? Each drawer is exactly 1 byte. That's why I was talking about the bytes thing. Each of these drawers is 1 byte. So 1 byte. Each of these drawers is 1 byte, right? So you need to understand that. That's very important. So what happens, these shelves, right? They store remember we talked about storing the program inside main memory. So it chooses a random, any drawer to use that's available, right? Then it stores the app in there. Then when the CPU wants to run the app, it's going to go read the main memory. So let's say the app codeblocks.exe is stored in there. That's literally how the main memory works. Then maybe in the next shelf, you stored the value of some variable, let's say 120. So that's basically how the main memory works. You can either store a program there or load the data to store data there. So we will use it in our case to store data because we are not doing very advanced things. So we're just gonna use it to understand that it stores data. Then what happens that you see that these shelves, right? They're able to store variables. And I'll reiterate on the fact that a variable is nothing but a box, right? A variable is nothing but a box. So with that understanding in mind, I'm gonna enlarge this. I'm gonna enlarge this to be able to fit in a box, right? Even if it's like a small box, that's fine. Because variables, that's all they are. It's just boxes that store something. And then those boxes, we can give them labels, which is basically the names of the variables. They'll be used to label the box. Remember, each is 1 byte, right? Then each of these drawers or shelves, they can store variables, right? Imagine these boxes are our variables, right? So in each shelf, we have a variable stored in there. And each shelf has an address or a location of where it's stored. Just like if you want to go visit Chomi, you say, Chomi, send me your location. Like Khalid once said, send me your location, that song. So Chomi is gonna send you their location, then you go visit them, right? So you're gonna go to where they stay and you expect to find them there, right? Just like you'd expect to find this box there because that's where it's stored at that address. So since each and every cell or each and every shelf or cell or whatever you want to call it, it stores a variable and it has an address. The address, the way it uses the address, the way it comes up with the address, it uses what we call hexadecimal. That should be familiar with you guys because you did it in ComSci 1B, which was last semester. Yeah, that's if you didn't add an extra years. Yeah, that happens a lot. So it should be revision this time around. So I'm gonna paste this. So it'll be having each shelf has its own address. But to be actually quite accurate, if you want to be really, really accurate, it is not the whole truth. If you get what I'm saying, this is not the entire truth. The address is right. What happens is that I know it's gonna be weird to model this thing, so let me try to minimize it. Okay, I would have to decrease the font, but that's fine. I'll just put an arrow here. So what happens is that each shelf, okay, once doesn't want me to, let me see if I can, yeah, but it's supposed to be actually here at the top, but it's fine. But each shelf, right, or each cell, it actually keeps track of the starting address. And then it counts how many, it adds bytes to that address. So if it's 1 byte, so I want you to notice the last numbers, right? It says 23. So if this whole thing is 1 byte, that means it's going to start at 23 at the top corner there, at 23. And then here, by the time it reaches here, no, it shouldn't be there. Okay, technically it's there, right there at the bottom. You should just add 1 to this 3. So the address here should be the same thing, 0x1f1. The only difference is these two numbers. It's going to be 24 because it's the whole cell's 1 byte. So when it counts the addresses, right, it counts with the bytes, which is the size of each cell. So if it's 4 bytes or 3 bytes, that means it's going to add 3 to 23, or to this hexadecimal, add 3. That means the last address here is going to be 01F126 because 23 plus 3 plus 3 is 6. So the last value is going to be 6 because we're adding 1 byte every time we went down the ladder, right, or down this thing. But then we in the textbook they don't like to mention that. The information I gave is important if you're doing C++ because you'd have to understand the actual way they represent the addresses. So I'll just say 45 here, different value or whatever. So now each box here when we specify what we call a data type and the name of the variable, this is what the computer does. The name of the variable, let's say call it num apples, right? Meaning this box, it stores number of apples. So that means this box will have a label that the variable name would act as a label for this box, right? As a label. Then the data type will act as the sort of like a restriction. It specifies what type of things are acceptable inside this box. For example, int, meaning you can only store integers, basically numbers that are part of the element of Z, right? Integers. I'm not talking about it mathematically, but element of Z. So here this will be a data type. So let me choose another color to distinguish it. So apply. So this will be the data type, right? It means that the only acceptable things in this box are integers. You try to do spiritual things and you store strings, crash. That's why it crashes, because whenever you create a variable and you define the data type, what Java does is that it's going to choose a random cell or a random shelf inside main memory and create a box there. But then most of the time, the box is already there. You just need to define or decide how big the box should be and things like that. So, and then you define the data type and you give the variable a name. So that why do we give a name? If we didn't give the name, we'd have to refer to that location by address, of which to be honest, we won't know. Because what happens with the computer, right? It keeps on changing addresses. So this address was used there, all of a sudden it gets used down there. So now you see that we might mix up our boxes, which is not what we want. So that's why we give it labels, so that even if the box is now in this last row, in this last shelf, we can still access it because the right box, because we gave it a label. It's just like you are in a garage, right? And you have a bunch of boxes. If none of those boxes have labels, it will take you forever to find what you're looking for, because you're gonna have to open every single box one by one. But let's say you're simply looking for apples. If it's written number of apples or apples, you know, oh, this is a box that has apples. And then you open inside, you expect to find apples because it is a label outside, right? So this label, it makes things easier for the programmer. The computer couldn't care less. The computer uses addresses. So just keep that in mind. And we're going to now talk about, since we understand, I did mention that if it says int, that means you cannot put a string or something that does not look like an int. So you cannot try and put this into the box. That's when Java is going to show you red lines. It's going to start screaming at you like, what spirituality are you trying to implement here? There's some third eye shit over here. What are you doing? Then it's going to complain at you. So yeah, be sure you understand data types. The data types is called data types. Even the word itself is self-explanatory. Data type. Flip them around, it's type data, right? Which just means the type of data the variable stores. That's literally what the data type is. That they name the people who invent things, right? They name them deliberately. So always be aware of that. So since we understand bits and bytes and all those things, let's understand data types. Let's start with data types, then we go to variables, right? So we have different data types in Java, but before we understand data types, let's try. I don't think it's necessary. It's not really necessary, like 100%, but it's worth understanding. So in terms of bases, right? A computer uses what we call base 2, right? You might ask why base 2? Because there's a set of two numbers that can represent any number in that number system. In this case, it's 0 and 1. So to represent literally anything inside this number system, we use 0 and 1. We'll talk about how to represent characters when we get to that chapter, which is the evening chapter, when you talk about strings and chars, right? I'll leave those types for that lesson. So for this, when I mention the types here, I'm gonna purposefully leave them out, char and string, because we're gonna talk about them in the evening class. So base 2, why is it base 2? Because there's two numbers, there are two numbers that can be used to represent any number or anything inside that number system. We use what we call base 10, right? Or DEC or decimal system. DEC meaning 10. Why 10? Because we have these numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? For example, I want to represent 950. I use the digit 9, and then I use the digit 5, and then I use the digit 0. Then I got 950. So that's what it means by bases, right? So in order to calculate and things like that, just simple. Oh yeah, I need to explain this because I'm going to talk about the ranges of each data type, and I'm going to use base 2. Yeah, this is very important. Yeah, I need to explain this. I just remembered now. When I was teaching ComSci 1A students this, I remember this is very helpful. So why base 10? That means when representing any number, we use this as the base. Remember the high school, you have base n to the power of some exponent, right? If you remember that formula, basic maths. So if it says base 10, that means we're going to use base 10, right? So let's say we want to represent the number 123. How would you represent that? We split it up into tens, hundred, thousands, and units. We split it up, taking you back to simple maths, high school. So it's going to be 100 plus 20 plus 3, right? Simple maths. Then I'm sure you can notice something. So far, we're dealing with a lot of maths. ComSci is maths. So if you don't like maths, you're in the wrong place. ComSci is maths. Everything is maths. ComSci 3A is literally based on discrete maths. Like the whole thing is based on discrete maths. So yeah, you can run away from maths. It's everywhere. You go to engineering, maths. You go to actuarial, WES. You go to other streams, economics, all this. There's maths everywhere. So 100, how can you represent 100? 100 is basically 10 by 10, right? Plus 10 by 2, right? Plus 3. We're just going to say plus 3 for now because I haven't introduced the bases yet. But 10 by 10 is basically what? 10 squared, right? And then 10 times 2 is basically 10 to the power of 1 times 2. This is basic maths. I don't expect, unless you're really that stupid, I don't expect anyone to be asking questions and getting lost here. This is very basic maths. And then you have 3 times, what are we going to times by? Because we want to times it by 1 so to get 3 back. Remember, any number to the power of 0 is equals to 1. So this would be base 10 to the power of 0. And then I've represented 123. So they never taught us in high school, but this is how the decimal number system worked. You had base 10 everywhere. Any number you represented with base 10, as you can see. And as you can see, there's a pattern. Starting from the right-hand side, the units, right, or the single digit, you say to the power of 0, then to the power of 1, then to the power of 2. You see, it increases by 1 going to the left. So you start from the right, right? If you check here, you start from the right, which is power 0, then to power 1, so be power 2, power 3, power 4. It increases by 1. This exact same philosophy applies to binary, but the difference now is the base. So if I wanted to find out this number, 111, right? This will be 1. Yeah, we can view it in this way. You can say 1 plus 1 plus 1, right? I don't know how that would work, but yeah, just view it in that way. It's 1 plus 1 plus 1, right? Then we look at the positions. This is position 0. For all number system, even octal, it's the same thing. You represent it the exact same way. Even hexadecimal, every number system is represented using this system. You just need to know what base it is. If it's in hex, that's base 16. In oct or 8, that's base 8. So you can expand your knowledge to all those other number systems. So this will be 1 times, but remember here we said times 10 to the power of 2 because this was what? Base 10. This is now base 2. So base 2 to the power of 2, which is 2 squared, right? This is the first answer, right? Plus basically what I'm doing right now, I'm unintentionally doing it, but it's converting binary to decimal. But in the midst of converting it, I'm also explaining a number system and bases. So this will be 1 times, you see, this is power of to the power of 1, right? So 2 to the power of 1 plus 1 times 2 to the power of 0, because remember, any number to the power of 0 is just 1. Then now this would just be 1 times 4 plus 1 times 2 plus 1, right? Remember BODMAS, when we start with brackets off, that's what he did, if you notice. We started handling whatever's in the brackets first. So brackets off, then division, then multiplication, then addition, then subtraction. So I'm going to start with multiplication, right? So this will be 4 plus 2 plus 1, which is just 4 plus 2 is 6 plus 1 is 7, which is just 7. So actually this number is actually 7. It's the decimal number 7, but in binary. So since you understand bases, that you always say base to some exponent to represent the position of the number. You start counting from position 0, position 1, position 2, and so forth in any number system. So now we understand that. Let's talk about data types and their ranges, because their ranges, they are measured using the base for that number system. That's why I was explaining the bases here. So to find the range of values a data type can store. You might ask yourself, why do we have many data types? Because each data type has a different range. Taking you back to high school, if you remember domains and ranges, that should be something that you know. I don't have to explain that. So find the range of values. To find the range of values of a data type can store. This is the formula, right? You're gonna say -2, right, which is the base, minus base 2 to the power of n, minus 1, if I don't mistake, yeah, minus 1 to positive 2 to the power of n minus 1 minus 1. That's the formula, right? This minus 1, we're subtracting the 0. We don't want to include the 0 as part of the ranges. By 0, it's like if I have minus 1, 0, 1, 2, 3, this minus 1 subtracts this 0. It shouldn't be included as part of the range. If you want to know why they do that, go ask the engineers, because this is as software engineers, right? Remember, there's people who make the hardware, which is the engineers, right? Who make the physical parts of the computer. Then there's people who just use them, which is us, the developers. Us, our only goal is to abide by their rules. The people who made the hardware, they know what they mean when they say subtract 1. You have to follow that. If you want to really understand that, trust me, you're gonna go some deep rabbit hole, and it's not gonna be nice, because now you're gonna have to go and understand a whole operating system, which will take a very long time to understand. So this is always the formula for representing any range, where n is equals to the number of bits. By bits, remember binary digits, meaning the number of zeros that can be represented, right? So we have these are the data types that we have, right? So Java. So these are the data types we have. We have int. Okay, let me start with byte. So we have byte, short. This is the integer data types, right? So we have, we have, before we talk about that, we have primitive types and we have reference types. The reference type is basically an object. That's reference types. For example, a string, we have a class called string. That's why we're able to call functions on a string type or string variable, because that's an object. It's not a primitive. Primitive type, or another word for it, they're called fundamental. Fundamental. In a way, you can view them as the languages that come built into the language, the data types that come built into the language. Remember, the string, it might come with Java or whatever, right? But it's not built into it. It was made by Java developers. Then they said you can use the string class. It didn't come built into Java. There's a difference. Some Java developers just implemented that class and they said, oh, since you guys work with strings a lot, let's create a string class. So we're gonna have the integer types, which is byte. I'm just gonna say integer types, which is byte, and this is from this is in ascending order, right? So byte, we have a short, we have an int, we have a long, then we have floating point types, right? Which is float and a double, right? We're not going to talk about char. Okay, Boolean, we could talk about it, but not really. We're going to, okay, today we'll cover if statements. So we'll talk about Boolean when we get to if statements. So here we're talking about just numerical types. Then we'll cover char and strings tonight. So byte, right? It has how many bits to represent it? It has eight bits. Remember, we talked about this is revision. This is a byte. If you remember this word, we did talk about it. I don't know where I put it, but I did mention it. Yeah. So 8 bits or 8 binary digits is equivalent to 1 byte or to a byte. So we actually have a byte data type inside Java. So it's 8 bits. Then we have a short, right, which is twice the previous size, the previous data type. It's twice the size of the previous data type. That's how it goes. So it goes in this direction. So we go from byte to short to int to long. Every time you go to the right, it's a bigger size, and you times 2. You take the size of the previous data type and times it by 2 to get the size of the current type. So if this is 8, 8 times 2, this will be 16. 16 times 2, this will be 32. 32 times 2, this will be 64. Simple as that. So that's how I remember it. So 32 bits and then 64 bits. Then now to find the ranges, right? How would you find the ranges? Because now you know n. Remember, you now know n. So this will be 2 to the power of n, which is the number of bits, which is 8, right? Minus 1, because you have to subtract 1. Then 2, right, to some positive value, which is a positive base 2 to the power of, because remember we explained here that you can convert a binary number to a decimal, right? So this formula is here, right? They'll give you decimal numbers, literally the numbers that you know that you can be represented by each of these types. So we have this, and then we have 2 to the power of 8 minus 1, minus 1. Minus 1, you subtract the result of this whole thing. Then you just do the same for all the other types. But instead of 8, you put 16 or 32 or 64. Pretty much the same thing. Then for floating point types, right? This is 32 bits, right? IEEE, right? It's IEEE what? Is it, I forgot, it's IEEE 7. I forgot what it's called, but it's IEEE. Yeah, of which the IEEE, right? It just stands for, I hope I still remember it. It just stands for Institute of Electronics and Engineers. Something. I forgot the E. Uh, Institute of Electrical and Electronics. Yeah, I think it's Electrical and Electronics Engineers, right? Basically, these are the people or engineers who came up with the formulas on how to represent floating point types inside a computer. They built the actual hardware. So that's why we say it's 32 bits of this standard. It's maintained by that community. You can, if you want to write for those people who are avid readers, you can go Google it and say IEEE, right? There's the institute, then you go there, you learn about it. Yeah, what is it called? I think I was right. Institute of Electrical and Electronics Engineers, yeah. Institute of Electrical and Electronics Engineers. These are the people who came up with the hardware or the formula to represent decimal numbers inside a computer. If you remember maths, pure maths, there's no one who's doing computer science who did maths lit, so everyone should understand that. So in pure maths or physics, you're taught about what's that thing? Scientific notation, right? So for example, if you have this 1.74, right? Yeah, I didn't do physics, so I'm not really that good in these things, but I think I still kind of remember how it works. So it represent basically scientific notation, right? It's a way to represent very big numbers using very small numbers. That's all. That's all there is to it, to that technique. That's all it does. So the engineers, right? Remember they're called engineers because they know science, right? So they applied, like I said, always relate the things you're doing in comp sci to the real world. They applied the concept of scientific notation to represent floating point numbers. So, for example, if you want to represent 1.74, right? This is already fine. Yeah, I think this is already fine. Let's say you want to represent 10 or I don't know, I forgot this thing, but let's say you want to represent 10, right? As a floating point, or it does depends whatever number you want to represent. You'd have to shift the number to the right hand side, right? It depends on the numbers you're working with. If you have, for example, this one, right? 0.74. This is different because now you're shifting it to the left, not to the right. And where are you shifting it? After this decimal point. That's where it's going, right before this digit, right? So if you're shifting it to the right, towards the right, you're gonna use a plus, right? Um, you're gonna count how many times, how many digits you flipped that side. If it's 1, then you're gonna say times 10 to the power of 1. If it's 2, you're gonna say times 10 to the power of 2. So this will be 1.074, right? Times 10 to the power of 1, right? Of which in Java, you can represent this as 0.1.074 E, right? E, you can imagine E just means 10, what it just means 10, it just means times 10 to the power of something. So you can imagine there's an invisible X here or times there. And then this E just represents 10. And then here you can specify the exponent after E. You can say 2, so this will be 10 to the power of 2. If you say 3, this will be 10 to the power of 3. So in most of the time, it's up to you. You can also represent whether it's positive or negative, saying positive 2 like that, meaning to the power of positive 2. Or you can say to the power of negative 2. You can represent it in that way. In our case, it's to the power of positive 1, right? Because our exponent is 1. Basically, we've moved 1 digit to the right. And you use positive numbers if you're moving digits to the right. If you're moving them backwards, you can imagine, or you can think of it in terms of walking. If you're walking forward, right, imagine is that positive, right? Meaning that's the way human beings are wired to walk. They only should walk forward, which is like positive movement, right? Walking backwards is like the inverse of walking forward, right? So minus. So you're gonna subtract. So this would be, you have to shift this digit to that side. So now instead of 0, there will be a 7. So this will be 7.4 times 10 to the power of minus 1, because I've moved 1 digit to the to the left. And I'm moving left, meaning it's sort of like you can picture it as walking backward. So it's an inverse of something. So you're typically going to use negative numbers for that. Or in Java, you can represent it as 7.4 E minus 1. You can use a smaller e or uppercase letter E. That's up to you. Either way, that's fine. So this is how the numbers are represented inside a computer. And as you know, I'm sure you've noticed something. we are moving. You see this digit, it moved to the other side. It moved to the other side. Even the 7 moved to another side. So that movement, right? You see that movement, the engineers, they used that movement of just moving that number. They call it, we floated the value. The value is floated, right? So hence they call this technique floating point types, because we are using scientific notation which moves values or floats values. So that's where they got the floating point term or terminology, to why they're calling it floating, because we float values or we move numbers if you are representing it in scientific notation. I hope that makes a lot of sense now. Yeah, if you check the textbook, they also say it's IEEE, so you need to understand that. So now to declare a variable, you declare it like this: data type space followed by the variable name. Since we now know the data types, right, that we're going to work with for numerical based things, right? Average, sum, all these things. That's the data types I've listed so far. We need to understand how to name a variable. What are the rules for naming variables? Remember, this will be in the exam. They might ask you, list these 2 properties on naming variables. Variables, right? When you name variables, you cannot use reserved keywords, right? Reserved keywords, if you understand English, you see, it goes back to understanding English. If you understand what this word actually means, you'll know that, oh, reserved, it means that it's reserved for something. It's like, you can think of it as like booking. You can't book a spot or a table in a restaurant that's already booked. It's already booked, right? You can do that. You can use it or book it. Same applies with variable with the naming variable. There's already keywords or things that are part of the Java syntax that are already reserved for something else. In this case, it could be int. It's reserved for declaring integers. For is reserved for declaring for loops. So you can't name a variable for, because Java will be confused whether you're trying to create a variable or a for loop. And it's going to assume you're trying to create a for loop, then it's going to complain that you're missing the round brackets and the curly braces and the semicolons, all those things. So that's why we never use reserved keywords. They're reserved for something else. It's already booked for something else. Then we have another rule that says your variable can be of any length. But don't abuse this property, right? Because if you have a variable like this, right? So let me make an example. If you have a variable like this is a very very long variable name to use. Imagine you're trying to use this variable in your code. There's no way you're gonna be able to type it. You see, you're making life difficult for everyone. Don't be difficult, or else you might lose your job. They'll be like, hey, this guy is difficult to work with. Then you get fired. Don't be naming things like that. Don't be doing spiritual things. That's a very long variable name to use. So don't be doing that. Don't abuse it. Then your variable, right? Variables can contain letters, digits. So it can contain letters, meaning letters of the alphabet, right? That's what I mean by the alphabetical letters. Don't think of any other thing, only of alphabetical letters. It can also contain digits 0 through 9, or an underscore, or a dollar sign. It can contain all those things. But even though it is legal to name all those variables like that, don't include an underscore. Okay, your variable shouldn't start with an underscore. It shouldn't also start with the dollar sign. Why do we avoid those? Because most compilers, when you install a compiler, it comes with variables that are declared with these things. You might mistakenly redeclare the same variable that's already part of the compiler, then it's gonna mess up your compilation and no one will be able to figure out what went wrong. No matter how much you try to pray about it, no one will ever figure out because you're doing spiritual things that none of the lecturers have ever and will never do. So don't be doing spiritual things. We are being told that it's valid just in case you're tested in the exam. They give you examples of variables. They say choose the ones that are valid. It is valid, but doesn't mean you should use it. You just need to understand what counts as valid. And then one last rule that it's not really a rule. It's you know when someone tells you something, right? For example, when your parents tell you you should do this, you should do that. That's a rule. But then when someone says, let's say a friend advises you, it's like, I think you should, or I don't know, it's up to you. But I think if you'd done it this way, it would be better. It's sort of like that, the thing that I'm about to list now. It's optional. You don't have to do it like that. But it's advised because all of them, yeah, all Java developers, like professional Java developers, they use this way. Use camel case to name your variables, right? What is camel case? Camel case, I did explain it to my first years. It's called camel case because when you take a line and you start drawing it, it looks like a camel's hump. You see the camel's hump, it goes up and down like this. When you start to take a line, it kind of looks like that. So let me show you. Let me open Paint, and I'm going to use camel case to name my variable, right? Then I'm going to try to insert text, right? So I'm going to install text here and say number, number of students attended, right? Did it save? Okay, this thing is its own with number of students. Then let me stretch it a bit. Number of students attended, right? Yeah, so this is the variable, right? Don't mind me with this, don't mind the Paint or app. It's not that clear. It is not that perfect. So I'm gonna draw a line here, and you should be agreeing with me that it starts to look like a camel's hump, right? When you go down like this is a capital O, there's a capital S, and then you go down like that, and then there's a capital A, you go up like this, and then you go to that side. Remember, I was supposed to make it a bit like a hump, yeah. So it's like that. So you see that looks like a camel's hump. That's why it's called camel case. Because when you put a line on all when you put basically you put humps where you see a capital letter, it mimics a camel's hump. So that's why it's called camel case. So I hope that's clear. It's advisable. It's not a must. It's not a rule, but it's advisable. Then yeah, that's all you have to know about variables. We'll talk about functions when we get to those, how to name functions. But you name functions the same way you name variables. You use camel case. Different languages have different philosophies. C# uses Pascal case, which is still like camel case, but instead of making the first letter small, uh, uh, what is making the first letter of the first word small case is no longer the case anymore. No pun intended. You're gonna capitalize it. So you'd have to capitalize every letter, number of students. So this is what we call Pascal case. So there's languages that do use different philosophies. You need to understand the language you're working with. We're working with Java here. We're going to use camel case. So this is how you declare your variables, right? So to declare a variable, you simply use the data type, let's say int, followed by a variable name. And another optional thing, use meaningful names for your variables. So instead of num s, I don't even know what that's supposed to mean. You should right number of students. This is more readable than nums or ns. I don't even know what that's supposed to mean. Number of sequences, I don't know. Yeah, you see, it leaves room for assumption. You don't want to make people assume. So don't call it ns, don't call it nums, right? Don't call it students. I don't, num can be something different. So just write it in full like this, number of students. Simple. That if you read the textbook, it tells you exactly, and I think it uses the same example that I'm using. If you read the textbook. So that's why my variables will tend to be long, but then they're straight to the point. So if you have number of students here, that's the variable. This is how you declare it. Don't forget to terminate or put a semicolon there, which means that this is the end of this statement. It's like a sentence. Sentences in English, right? We put in a full stop, right? In Java, instead of a full stop, we use a semicolon. If you forget the semicolon, computers are not lenient like human beings, whereby you can let things slide. If you forget the semicolon, it's not going to run. So make sure you put the semicolons after every declaration, every time you declare. What if you have multiple variables of the same type? You can actually initialize them, create them, all of them separated by comma. So you can say x, y, z, like this. So this is the same as saying int x, int y, int z. Then you can also give them initial values. That's up to you. You can say this is initially 10, and then so all the other ones won't have default values. So you can declare it in whatever way you feel like declaring it. That's up to you. 9. So this would be the same as putting it in a separate line. But then now instead of doing that, do it in one line. Then you can also initialize this variable. Just make sure whatever value you use to initialize on the right-hand side of the equal sign is the same data type as int. You need to understand also things that we call literals, right? So this is an integer literal, which just simply means it's literally an integer. That's all they're saying. So if you were to put a dot, the moment you put a dot, Java interprets it as a double, which is wrong, right? Let me show you why it's wrong. You can, right? I needed to explain something here. Each literal has a suffix, f, a small letter f, or capital letter F. So each literal you create for a float, you need to add that F at the end. It's either a small letter F or a capital letter F. Even for long, you have suffixes, right? Which can be an L, small letter L, and then a capitalized L. We always use the capital L because you don't want to confuse the small L with the 1. So you don't do that. And then for doubles, it's optional. Doubles is optional. You can append a D, small letter D, or a capital letter D. It's there in the textbook. You can go confirm it's there in the textbook. I'm getting all of this information from the textbook. So there's your variable. So what happens is that Java sees, oh, this is Java. This is not what Java sees, that this is a double. Then when it sees a double, it sees how much, it looks at how many bits are there. Oh, 64 bits. So what you're trying to do is this. You're trying to store something big, 64 bits, into an int, which is 32 bits. That's what Java sees. That's why it's gonna crash and say, this is impossible. What you're trying to do is impossible. You can't fit something this big into into something this small. So some casting is involved. It has to be involved. So we have to do what we call casting, basically to force Java to interpret it as an integer. That means it's gonna discard from the point. You see, from the dot, go in that side. It's gonna delete all of those things, and you're left with the number in front of the dot. That's basically how it's going to cast. So that's casting. I think I can give you an example of, I can show you the example. To cast, you just put in the data type inside round brackets, and then you put the cast right in front of the variable. When you're dealing with literals, like meaning you type the actual numbers, don't be stupid. Don't create the literal, then cast it. That's very stupid. You can just simply declare the number as it int. Don't be doing spiritual things. Casting is only meant for variables. For example, if I'm taking a variable, let's say it's double average, right? And I have an average here, right? There's no way I can say, let me delete the dot and every number after the dot. There's no such thing. That's why I have to cast. Casting is only for variables, not for literals. So this I have to put an int here. What Java does, right? It's going to be like, oh, so if this is 64, that means 64 is basically 32 plus 32. That means 32 bits plus 32 bits. That means I'll simply lose those 32 bits or other 32 bits, and then it deletes them. But then it doesn't change average. It just means for that time in line 88, for that only that time, treat average as an int. That means it has to be reduced in size because it's too big to fit in there, right? So it has to be reduced to 32 bits first. After it's reduced, then it can be stored. And it's going to drop whatever numbers was there that doesn't look like an int. So for example, if this is 123, comma 50, what happens is that it's going to go to this variable, replace the value inside the variable in that location, like this, to 123.50. Then this cast will discard everything from the dot going to the right. So that means this will just be 123. And the process of it deleting the dot and everything, that's when it's actually changing the size because it's too big to fit into an int. So I hope that makes a lot of sense. Then now we're gonna talk about our operators, right? There's not a lot of examples there's no need for me to use all the data types. Use your imagination. If you want to work with shorts, this would be a short. There's nothing new about that. So I'm just gonna choose int and double because that's the types you guys will mainly work with. Then we're gonna talk about the operators, right? We have the arithmetic and the logic. In our case, we're not dealing with logic yet, so we're gonna talk about arithmetic. So we have the plus, which just means to add, addition. Then we have the minus, which just means to subtract. Then we have the asterisk, right, which just means to multiply or multiplication. Then we have the forward slash, which just means to divide. But this divide over here, right, you need to be very careful. Remember, we talked about, you see, this is the important part that's the reason why I was explaining how the CPU works. If you go back to the top here, right? Like I said, this session was going to be a lot of theory. So just bear with me. So CPU is the central processing unit, right? We say that it does the arithmetic and the controlling and the logic and everything. And we said it can only add things that are of the same type, right? Just remember that. You can only add things that are of the same type. Don't forget that. So that means if you have a division and you're dividing an int divided by an int, you don't actually get the number you'd expect. You get what we call the quotient, meaning it's not a double. You don't get back a double because the processor or the CPU, it took in two integers. Obviously, you're going to get back an integer. You can't give me cooking oil and then all of a sudden, after I've cooked using cooking oil, all of a sudden the pot has stay soft. How is that possible? So the same reason why that's impossible, it's the same reason why it gives you back an int. If you're doing a division on two integers, you'd obviously get back an int. You can't get back a double. That's weird. If you want to get back a double, meaning quotient plus the remainder, you have to do the double division. How do you do that? through casting. Like I said, if you're not working with literals, you only do casting if you have two variables. For example, you have what is this? Total, right? Divided by 10 pregs, right? You guys are gonna do 10 pregs. This will be your total for all the pregs divided by 10, so to get an average. So you don't have to do spiritual things. Hey, you guys like doing some spiritual things. I don't know why. You don't, this is very spiritual. If I was marking your code, I'll give you a 0 for that part. I wouldn't even tolerate nonsense like this. So you don't do this. If you do that, yeah, if I was a lecturer, I'll say, come see me in my office. This is a literal. Use common sense. You can simply add a dot and a 0. It becomes a double. So what happens is that when the CPU sees, oh, this is an int divided by a double, it looks at which one is bigger. This is 32 bits. This is 64 bits. Obviously, the double is bigger. So therefore, it's going to promote this one, the first one, this int to a double. So it means it's going to add an implicit or an indirect cast. You won't see it, but it's going to add it. So here it's going to add the cast to a double, which just simply means make this 32 not this 32, this integer, just add a dot 0 somewhere there, right? So if for the first part of the integer, I have my number of, you have 10 practicals, it should be around 1,000 there. He provided that each prac is 100, should be around 1,000. Let's say you got 98. So the computer, when it sees this integer divided by this double, these are two different things. CPU can only do arithmetic on the same types. So it promotes one of them to be the bigger one, whatever the bigger one is in the case. So how does it cast? It's simple. It just simply adds a dot 0. Then it does floating point arithmetic division. So basically, it's going to give you back a number with a dot. So this will be 98.0, right? So this is going to give you a double back. So that's how you gonna do proper division. You just treat one of the numbers, whether it's the numerator or the denominator, you treat it as a double. Then the computer will do the rest. It will promote the other one that's not a double to be a double. And if you didn't know, I know. So you need to pay attention of something here. Float is 32 bits IEEE, right? These 32 bits, remember these 32 bits also include the decimal point, basically remainders and stuff. So float will always be bigger than any of these numbers. Float is bigger than a long, also bigger than an int. Even though int is 64 bits, it's bigger. So just keep that in mind. So if you're doing division between a float and a long, and you be like, no, it's gonna promote it to a long, you're wrong. Because the float, it's 32 bits, but remember it also stores the remainders. So it's actually bigger than this. So this long is the one that's going to be promoted to a float. So if you want to rearrange them in the right order in terms of smallest to biggest in the data types, you start from byte to short to int to long to float. And then the biggest one will be the double. If the type you're trying to convert to is on the right-hand side, then it's going to do what we call an implicit cast, meaning it's going to do an indirect cast. Because at the end of the day, the size is bigger. So that means it can accommodate that size. So if we are casting from an int to a long is bigger than an int. So that means the int will definitely fit into the long. But if you're going in the vice versa direction, from long to int, long is 64, int is 32. So you see the problem there. So it forces you to do what you call an explicit cast. Basically, you have to put in those round brackets, then you say cast it to an int yourself because it wants you to take full accountability of what you're trying to do. Because when you cast this thing from a long to an int, you're gonna lose some information because this is 64. That means you're gonna lose some 32 bits of information. So it doesn't want to be responsible for that. It'll tell you, no, if you wanna shoot yourself in the foot, you do that. There's the gun, shoot yourself. Me, I'm not gonna be liable for anyone's issues when the assignment doesn't run the way you want it to run. Leave me out of it. You do everything manually. But then if it's wider, then it will promote it for you. You don't have to cast. I hope that makes a lot of sense. Then we have modulus. If you're doing discrete maths, this is modulus, right? This is sometimes called this is under the topic inside discrete maths, modular arithmetic, which is horrible. I don't like this topic, which is horrible. But yeah, you'll survive if you are doing discrete maths. You'll be fine. Basically, this returns the remainder. If integer division returns a quotient, integer division with the percentage symbol is going to return the remainder. So this percentage symbol, it actually does integer division. And remember, if that's why you need to understand discrete maths. Remember to when you're doing division, right? When you're doing modular arithmetic, both the numerator and denominator, they should be integers, both of them. If for some weird reason you do spiritual things and you put a float, crash. Yeah, I don't think it will run. Most definitely sure it won't run. This operator over here only works with integers. So basically you only do integer arithmetic here. No floating point is allowed. Because why? A remainder is going to give you back an integer, right? Remember we talked about the CPU, that it only uses this, does calculations on the same types, then it returns that same type of those things you've done arithmetic for. So if you're dividing for integers, it's going to give you back an integer. Remember, remainder gives us back one number. So which is going to be an integer. If what's being returned is going to be an integer, 100%, it's 100% likely that the numbers we're dividing are both integers, because the CPU only does arithmetic based on the same data type. So this would be the operators. Then then after this we can talk about augmented I almost forgot, we have augmented operators, right? So augmented means that combined, right? So for example, if you wanted to say x is equals to x plus 1, this can be rewritten as x plus equals 1. That's what augmented means. So this would be an example of augmented. So the list of augmented operators are plus or equal, minus equal, divide equals. I'm sure you pretty much get the point. Modulus equals, those are the augmented operators, basically combined. They're called augmented in a way, which means combined. So this shortcuts, right? If you don't want to write this, but then just know it does everything that's on the right-hand side first before it adds or it subtracts the number itself. If you're using plus equals, that means you're adding x back to the result. If you're using minus, that means you're subtracting from x. If you're doing division, that means you're dividing x with the result, and so forth. So this would be the augmented operators. And then we're gonna now go to, this is gonna be, like I said, this session is gonna be very long. We are almost done. We're left with if statements. Then we're gonna call it a day for now. Then we see each other in the evening. So this is if statements, right? So we're gonna go to if statements. If statements are pretty straightforward. It's not that too complicated. So I don't think I should, but let me just do it, because I don't want to waste time. That's what I'm avoiding, but let me just do it quickly. Let me quickly do it. Where's this thing? Is it this one? See, I'm not used to this diagram, to these tools for diagrams. I must find a tool that I'm really comfortable in, then use that. Because I always have issues with creating these diagrams here. I don't find the right arrows and everything. Flow chart. Yeah, we see the decision. This is the flow chart thingy, but it doesn't have all the things that I want to list. It's fine. I won't draw the diagram. I'll just explain the if statements. Yeah, I don't see the symbols that I'm looking for. So if statements, right? If statements, there's different kinds of if statements, and if statements, their purpose, right, is to do something when a condition has been met or when a condition is true. We say that when a condition is what? True. In this case, we can think of it, for example, we always use if statements on a daily basis. For example, you check the weather, right, before you go out. For example, if it is raining, wear a jacket. Else, leave the jacket at home. So that's basically what an if statement does. You do something when a specific condition, we call that a Boolean condition, has been met. By Boolean condition, we mean that it returns true or false. So this is the syntax. You have if Boolean expression. I think it's expression, not necessarily condition. So expression. Then you have this. So this will be what I call a single if statement, right? Single if statement. So this runs when this part over here returns a true or false. So whatever true or false it returns, it stores it in a data type that we call bool, right? It's called bool for Boolean, right? Why bool? Because the person this um remember this is based on mathematics. The person who came up with the Boolean the maths behind Boolean or logic, all those things, his name is called George Boole. So you see, they took it from his surname, then they made a data type to honor him for what he has created, which has helped work develop logic is quite very important if you noticed in an app. Logic is one of the most important things. So they wanted to commemorate him on that discovery he did. So they named the data types are usually named after his surname. Oh no, what am I doing? It's Boolean in Java. This is for C++. Yeah, so they said Boolean in Java because this was Booleans, George Booleans. I hope you get it. You get English. If you're clubbed by English, that's a you problem. Go revise English. Try, what's that app? Is it Duolingo? Something like that. There's an app that teaches you languages. Go learn English there. So Boolean, meaning that it's a variable that can store only true or false. So stores only true or false. Literally true or false. Small letters, right? Don't try to capitalize anything. True or false. So that means this Boolean expression should return us true or false. And it's a data type, right? So you can create a variable. Like always, you can like we've always been creating. So you can create a variable called if is raining and you set it to true, right? Then here you just simply put that variable is raining. You use two equal signs to compare equality to check if two things are equal is equals to true. So that means it's true that it's raining. If it is raining, then you can output a message, wear a coat, something like that. But in Java, if it's like this, right, you can abbreviate it to just if it's raining. Then what Java does, it goes to this variable. It checks if this variable returns a Boolean, then it won't complain. Then it checks what value of a Boolean it has. Is it true? If it has true, then it's gonna run this part. So that's basically how you can avoid always typing equals. You don't have to always type that. You can just put in the Boolean variable there and then it works. Because Java will check its value for you. You don't have to use equals always. So this will be the single if statement, right? This will be the single one. Then we have the if else statement, right? And this one, remember this if statement at the top here. it only handles for the case when it's true. What about when it's false? Because it's not always the case that it's raining outside. Like today, it's not raining, right? So that means this statement will be false. So we need to also handle for when it's false. So you have a Boolean expression here again, which returns true or false. Based on what it returns, it runs something, right? So here executes if Boolean expression is true, right? It executes if Boolean expression is true. Else, it executes if that expression is false, right? Meaning, if I'm checking if it's raining here, that means the else part runs only when it is not raining. Basically, this part is false or gives me back a false. That's an if else. It handles both cases for when it's true and when it's false. A single if statement only handles for the case when it's true and neglects for when it's false. Then we have nested if statements, right? Nested if statements. It's nested, right? It's a nest, right? It's one thing, then another, right? So you can have an if statement here, then within here you have another if statement, right? With an else. And then maybe here you also have just one if statement. So this is what we call nested. You see, it's a nest. It nests. It's like it forms something, right? It's like it's a. But yeah, I think you should get what nesting means. So this is how an example of nesting would look like. Basically, if statements within other if statements. That's what we call nested if statements. This is very bad programming. Don't do that. It's just don't overdo it, right? Don't have after a year you have another if statement, after a day you have another. No, no. Me, I would mark you 0 for your lecture. I wouldn't play about that. Don't have time for jokes. If you think that's funny, you tell the next year's second years those that joke and see if they'll laugh because you've been in the same class together after repeating the module. Nested if statements, there's that. Then we have a multi-way if statement, right? If statement, this multi-way if statement, right? It's basically, remember, if you look at our types of if statements we have that we've mentioned so far, we have one that only checks one condition. Then we have this one that checks one condition, and if that condition is false, we do something when it's false. But what if instead of checking only one condition, I want to check multiple condition, hence multi-way if statement? So you'd have to simply say if some condition here, right? And then done. You execute here if that condition is true. Then you have an else if here, which just means else, right? This is false, but if check this other condition. So this is other condition. You check another condition, check if this is true. Then you can keep on, you can have as multiple else ifs as you want. That's up to you. Then eventually at some point you also need to include else and else somewhere. Right. So I'm gonna choose the mathematical representation of this. So I'm just gonna say, right, just know that there's more, right? There's more, there can be more else ifs going down like that. Then you're gonna have an else, which just means none of the above were true. That's when you use an else. Then that would be that if statement, right? Then we're gonna talk about switch statements. But before we talk about switch statements, let's talk about the logical operators, right? These are operators that we use in logic. There's quite a lot. Not is it Boolean or I forgot the right terminology for these things. I just call them logical because they all return true or false. So we have two equal signs, which just means left hand side. It checks if left hand side is equal to whatever's on the right hand side, and then returns true or false. True if they're equal, false if they're not. Then we have less than or equals to. We just checks if left hand side is less than or equals to whatever the value or whatever the result is on the right hand side. Then same applies to x greater than or equals to I hope you get, this one, it shouldn't be that hard, straightforward. Then greater than or equals to, then you have less than, which just means left-hand side happens to be less than the value on the right-hand side. Then you have greater than, which means that the left-hand side happens to be greater than the right-hand side. Then we have not equals. We use an exclamation mark followed by an equal sign, which just means left-hand side is not equal to. We're trying to check if they're not equal. So that means our goal is to make sure they are not equal. When it's equal, it's going to return false. So it should return true when they are not equal, right? So this means left-hand side is not equal to the right-hand side. That's the exclamation followed by the equal sign. Then we have other ones. Let me think. Then we have other ones whereby you have and, right? So you have and, which returns true if and only if left-hand side and right-hand side, they both evaluate to true, right? So you have true on the left-hand side and true on the right-hand side. That's the only time the whole statement becomes true. So, for example, if you have if it is raining and sunny, then you can simply say monkeys are getting married today. There's that saying. So that means both conditions need to be true. It needs to be both raining and sunny for monkeys to be married, to be getting married. Then we have two pipes, right? These pipes, I'm sure you are familiar with them with regular expressions. These two pipes, they mean or, the logical or, meaning that it can be one of them. So left-hand side or right-hand side. That's what it means. So if you remember your logic, go back to first year, go look at those slides. If you're a very forgetful person, go revise. Because other people, they remember these things. So you'll be the only one. Then we have not, which is just an exclamation mark. This just means not, which just negates, right? So true, it becomes true if there was a false. So okay, it's like this, not true is equals to false. And then not false is equals to true. That's basically what negation does, right? It just gives the opposite of that truth value. This true or false, we call them truth values. So it just negates the truth value. That's what it does. This not operator. And then that's pretty much okay. You're rarely gonna use it, right? You're rarely gonna use it, and I mean it. You have this thing called that looks like see, like you're trying to say an exponent to the power of something, that cap sort of. This means exclusive or, right? Meaning they're mutually exclusive. I don't have to explain that. Go revise probability. So this would just mean the way you find the result, right? It only returns true if there is different truth values. That's this formula. So if you have true, it's called exclusive or, but then the way you use it, you say X or R, right? That X standing for exclusive, this or standing for all. So if you had something like this, true, X or R, false, this will result to true because you have two different truth values. That's the formula of exclusive or. If you have the same, it results in false. So the only type is true is when you have two different truth values. This is rare. When I say this is very rare, this is a very rare operator that you can use, but it is useful. It's when two things are mutually exclusive, right? In this case, I'll just put it in this way. It's when two events, they cannot occur simultaneously. It's impossible for them to occur simultaneously, right? So, for example, you can't be having a distinction and failing. At least one needs to be true. So you can either be having a distinction and passing, or you can either be false failing. That means no distinction. So at least one of them has to be, they have to be different. They can't both exist. You can't be getting distinctions and failing. Those two events are mutually exclusive. They cannot occur at the same time. So that's where you'd have to use this operator. Only if you had a practical that requires for you to do that. Maybe we might. I hope Mr. Ofao makes it a bit challenging. He gives you a practical, like he puts that there, and you must know that you must use exclusive, or if you don't know, it's char. I hope he puts it there in some preg. So we understand the different logical operators, right? We have no, these are I remember they're called relational. These ones over here, they're called relational operators. Then these ones at the bottom, they're called logical, right? Because they're based on logic in maths, right? The topic logic. If you're doing, is it linear? Yeah, I think linear algebra. No, it's not linear, it's discrete. Yeah, discrete maths, they do revise thoroughly on logic. I think even linear, I'm not sure. But yeah, I remember discrete. They do talk about logic. So this is almost everything, but we're not done. We're left with switch statement and a ternary operator. I need to cover both of them. So let's just bear with me to finish up this thing. So we have what we call a ternary operator, or sometimes it's called conditional operator, right? It is one of those two names. So you do it asks a question, right? Some question, and then it puts a question mark. If you remember English, to ask a question, you put a question mark, right? Like I said, try to compare what you're doing in ComSci to the real world. You put a question mark, and then this is the part that you do something when that question happens to be true. You do something here. This is when it's true. Then you put a colon, and then you do something when it's false. But then by do something, right, a ternary operator is different. Here, it actually expects you to return some value. So it could be, maybe you want to change it to 10, or it's a string, or you want to change it to some char. So it actually returns a value. The ternary operator returns a value. So you can use a ternary operator like this. So for example, you can say Boolean is raining something, right? And then you initialize that Boolean to whatever the ternary operator returns. It can be any type here. Remember, any type here. But then this type that you're putting here, right, must match with the data type of the variable. Don't be putting 20 here and it's a Boolean that's it. It's going to crash. So yeah, be very careful of that. And it's true, right? I was just putting it there to let you know that this is a value that you return when this question happens to be true. So for example, excuse me. So for example, we're trying to change a maximum, right? So we have int max, right? We're trying to find a maximum between two numbers. So int a is equals to 20, int b is equals to 30. I'm trying to find the maximum. So I can say the max, you could do it two ways, right? You can do an if statement. You can say if my maximum, right, the current maximum that I thought was the maximum happens to be less than, it's up to you how you phrase the question. You can phrase it in this way, or you can say if a is greater than the maximum, you can phrase it in that way. That's also fine. Or vice versa, because look at this. If you read it from this way, go in that direction, this will be max is less than a. If you read it, go in that direction. So it's up to you how you want to phrase the question. So if that's the case, then I need to update my maximum to be a. Else, it has to be b. Right? So else max is going to be b. But then if you look at all this thing, right, you see all these lines, 1, 2, 3, 4, 5. 5 lines just to find the maximum. That's where a ternary operator can save you some time. So you can just say max is equals to, you ask the question, right? So what is the question? Is a greater than maximum or max? When that's true, update. Remember, whatever is returned here, right? Whatever is returned, whatever value I put here, right, in any of these parts where there's question marks, will be stored inside max. So if A happens to be greater than this, right, then this is the part when it's true. This is the part when it's false. I'm just showing true or false to show you that that's when the statement is true. I'm not saying it should always return true, the value of true. No, I'm saying when that question is true. So when that question is true, that means my maximum is no longer the current maximum, right? I have to update it to be A. So this means I must return A. Then this A, you see this assignment here. That A would be now stored inside this max variable. Else, store B into the max variable. Do you see how convenient and how short this is compared to all of these lines? So the ternary operator can be useful, especially when you find the maximum small codes and things like that. It makes it easy. So use it in those places. Then we have a switch statement. I'm not going to dwell too much on that. You guys know switch statements from C++, but they're different or compared to the ones in C++. The one in Java is a bit different. So you have a switch, then you have an expression here. That returns a value, or it can be some value. It can be an expression or a literal value. Then you're going to have cases, right? So you're going to have case that match, that checks what that value is in that, whatever value is going to be returned here. So for example, if you're doing game development in C++, if you remember, you'd have case A, small case A, and then case uppercase letter A and stuff, right? And then here you pass a variable like ch option, right? Something like that. And then what this does, right? If you notice the cases, what they're basically doing is this. They're asking these questions. Ch option, is it equals to small letter A? That's the question is asking. If that's not the case, it's fine. Check, because when you list them in that order, one after another, you're saying it's at least one of them. So here you are checking, if it's not equal to small letter A, is it equal to the capital letter A? If that's the case, then do something. Once you're done doing that thing, break, meaning leave the switch statement. So here you do something, right? When it's any of these cases, it's any of these. So that's where you need to understand things like or. It means that it's the value A, or is the value uppercase letter A. If it's not the case, it'll skip, right? It'll totally if it'll end here asking questions, then it's gonna skip and go after this break. It's gonna go after this break and then check the other cases until it finds the right case it matches with. If it's unable to find the right case, we have what we call a default, meaning when it's none of the above. You can imagine this is like an else in an if statement. It's like catch all, right? It catches, it handles for all the cases that didn't match, all the cases above that didn't match. So here you can, I don't know, output an error or something, that incorrect option chosen, something like that. So system dot err, which sends it to the error stream, standard error stream. So err dot println, then you output an error. If you still remember in C++, remember you'd call the exit function and you pass a number here, like -1, something like that. In Java, it's still similar, but it's now part of the system class. So system.exit. I just thought I would teach you this handy tool over here. So you just say system.exit, basically telling the operating system to exit with this -1 code, meaning something went wrong. Because all languages, they have a main function which returns 0 to the operating system, which tells the operating system, if you've reached that line of code that returns 0, assume that everything went well. So 0 means that everything went well. So if you return anything or you exit your application with a value other than 0, the computer or the operating system assumes that something went wrong. So that's why we would usually exit values that are non-zero, right? Basically it's not at 0. So this will be all the chapters 1, 2, and 3. Yeah. This will be chapters 1, 2, and 3. Yeah, I think they did talk about switch statements. Yeah. So this will be everything. Yeah, it's quite a lot, right? I'm sure there's a lot to take in. Your brains are tired. I'll make a PDF out of this. I'll copy everything and put it inside Microsoft Word, then send it to you via the group, right? So that's it for now. See you in the evening class. And yeah, homework. Yeah, I'll send you the homework in the group.